Pleased to have Nima Arkani-Hamed, who's going to talk about the Amplituhedron, and he promised to explain the titles informatively.
Well, it's absolutely wonderful to be back at the Simon Center, as always. Since I understand that this is that there's more than the usual number of mathematicians in the audience for a talk that I'm giving, I decided to take advantage of the wonderful culture of mathematicians, which is something I wish, I personally prefer a lot. And I wish we did more in physics, which is to issue these stupid laptop talks and give a talk on the blackboard. So I hope that is OK with everyone. I'm going to be talking about some work, which is, in a sense, the culmination of about 5 years of work on this general area. And I've the last step, which is what I'll focus mostly talking about today, is going to appear in some in a sequence of papers with my former student Yaroslav Trinka, greatly influenced by a paper we wrote last December with many physics collaborators, Jake Bergeli, Freddie Cachazo, who's played a crucial role in this whole subject, Yaroslav, as well as two mathematicians we had a wonderful, fantastic time talking to, Sasha Goncharov and Sasha Pasnikov, and which in turn goes back to some earlier ideas making a connection between the physics that I'm talking about and the Grassmannian with my now very former students, Cliff Chung and Jared Kaplan, as well as a postdoc at the Institute, Simone Caron-Huel. So what I want to talk about is what at least we feel are some beautiful new mathematical structures that in a most unexpected way connect to some very basic physics. They connect to the physics of scattering amplitudes, in particular scattering amplitudes in gauge theories. Now, scattering amplitudes are arguably the most important physical observable in high-energy physics. Certainly, they're the observable that our experimental colleagues measure all the time. We bang particles into each other, and the world is quantum mechanical, so we can't predict exactly what happens next, even if the initial state is exactly the same. But we can predict the probabilities for what comes out, or more primitively, the probability amplitudes for what comes out that we then square, or mod square, to get the actual probabilities. So on the one hand, they're the bread and butter observable of high-energy physics. On the other hand, they're also conceptually very important for a variety of reasons I won't have time to get into in detail, but they're one of the conceptually most important observables in a quantum field theory. And thinking about scattering amplitudes played a crucial role in the early development of quantum field theory in the hands of Feynman, Schwinger, Dyson, and their friends in the late 1940s and early 1950s. And if we think about scattering processes in perturbation theory, if there's a weak coupling parameter that we expand in, this is a problem that is in principle been solved for 60 years, over 60 years. So, and that's what made Feynman famous. Feynman figured out how to give a description for calculating scattering processes that had a purpose in life. What Feynman managed to do, and his friends, which wasn't manifest beforehand, is to give a description of this physics of calculating scattering amplitudes in a way that made the two twin principles of the two sort of foundational principles of modern physics of relativity and quantum mechanics, more specifically locality and unitarity, as manifest as possible in every step of the calculation. Okay, so that's done by giving a picture for what's happening as by drawing these diagrams as really processes that can take place in space-time. And because the world is quantum mechanical, we've got to add up all the different ways you have of doing it. So this is something which has in principle been understood for 60 years. And so people for a long time have had a feeling that where the mysteries in quantum field theory are in the places where this weak coupling expansion breaks down, in the strong coupling dynamics of field theories. And of course, there's wonderful mysteries there, and we've discovered a humongous amount of what's going on, dualities, the incredible fact that two different gauge theories can be the same. A gauge theory can be the same as a gravitational theory. These are all amazing facts about quantum field theory's strong coupling. But there's been a growing realization over the past 2 decades, and sort of accelerating more and more, that there's even something missing in our understanding of quantum field theory at weak coupling. And there's extraordinary, absolutely extraordinary structures that are sitting there in the structure of of scattering amplitudes and other observables, but we'll talk about scattering amplitudes today, even at weak coupling. Even at weak coupling, the standard way of doing things is concealing an incredible underlying structure in the final answer that's only evident after you've finished calculating everything and stare at the final results. And there are symmetries, there's simplicity, astonishing simplicity, and hidden symmetries that no one would have anticipated, that there's no technological obstruction to discovering in 1955, but which were only discovered in the 2000s. And so there's all this structure sitting under our noses for 5 or 6 decades that's starting to come to light. Now, a lot of this work, there's so many different threads in the subject, and this is not remotely a review talk. And there's this program going on here this entire fall, which is about many different aspects of these remarkable structures that are being unearthed in the structure of field theory even at weak coupling. But I want to tell you about one particular angle into the subject, which is the one that, as I said, I've been pursuing with a variety of collaborators for around 5 years, which at this point has some. Up to this point, it's been a story in search of an ending, and at least there's a local ending to the subject, so I can give you a relatively logical picture for what's going on. Actually, if I wanted to be a little bolder than I actually am, I could start the subject completely as a math talk. Okay, we would start by what we'll get to in hopefully 20 minutes or so by drawing pictures of triangles and polygons and generalizing them into the Grassmannian. And they're very natural mathematical objects. You might enjoy them as a mathematician. And we would gradually discover that the properties of this object resemble an awful lot those of scattering amplitudes of gauge theories. And gradually start developing a dictionary between the two of them. And really see the physics of scattering particles come out from a starting point that does not look remotely like it has anything to do with gluons propagating in space-time, evolving under some unitary Hamiltonian. And seeing how these ideas of locality and unitarity emerge from these more primitive principles that we'll start from. I'm not quite so brave, so I'll spend 20 minutes putting it in a little bit of context, and then I'll ask you to forget everything, at least if you're a mathematician, and we'll start from the beginning, and I'll just tell you what the structure is. Partially because the talk is also aimed more at the mathematicians in the audience, I'll ask you to believe certain claims I make about the physics that aren't very relevant for the discussion I want to have today. And mostly I just want to introduce you to this object and hopefully get some fraction of you interested in looking at it, because we could use the help in trying to understand what this marvelous structure actually is. Okay, but so before getting into that, let me just back up a little bit and tell you why we should care about this. I mean, there are these nice mathematical structures and scattering amplitudes, but so what? I can at least tell you my own motivations very quickly. And while we're talking about a very down-to-earth topic of computing scattering amplitudes and gauge theories, indeed, in some level of approximation, lowest level of approximation, literally these amplitudes are the things that are relevant for scattering experiments at the Large Hadron Collider, for example. There's a deeper reason I think thinking about this sort of thing is important, which is that for very well-known reasons that I won't go into here, having to do with gravity, and less well-known reasons, but still well appreciated for a long time, having to do especially with cosmology, we've suspected for a long time that these two, pillars of 20th century physics, locality, the picture of space-time and local interactions in space-time on the one hand, and the idea of a unitary evolution in an infinite Hilbert space, ultimately, to allow us to define sharp quantum mechanical observables on the other hand, that these two ideas are likely, at a very deep level, suspect. Certainly, the idea of space-time almost definitely breaks down. It's impossible to do experiments that can actually localize arbitrarily short distances and times because of gravity, and so it's been well appreciated for a long time that space-time has got to go, has got to be replaced by some more primitive ideas. It's even likely that, that because of much more confusing questions having to do with applying quantum mechanics to the entire universe, that making sense of quantum mechanics needs some extension. Not that quantum mechanics is wrong, but it needs an extension into situations where the usual quantum rules don't make sense, and we don't know what we're talking about. So that's very disquieting. These are the two pillars of our current shockingly successful description of nature, but we suspect that they have to go at some level. So what do we do? Well, there's lots of things. There are a lot of strategies that one can take. But we can take a little bit of inspiration from history. This is not the first time in the history of physics that we've been forced to make radical departures from previously cherished principles. We did it when we went from classical to quantum. We had to lose the idea of determinism. And you might imagine, how did that actually happen? Of course, in the usual history, we say it happened because experiments came along and people discovered quantum mechanics like that. But there's actually lots of clues to the fact that quantum mechanics was coming, sitting there in the structure of good old-fashioned classical physics. And if you imagine being a ghost of theorist future and going and telling a classical physicist in the year 1780 that in the 1930s determinism is gone, they could do two things with that information. They can't get back to sleep. So you can either try to guess what the right theory is. And there's no way you're going to guess the correct structure. You're not going to guess about wave functions in Hilbert spaces. It's too big a leap. You could do stupid things like add stochastic terms to Newton's laws to modify determinism in a dumb way. But things have never worked that way in physics. So it's much more subtle and interesting what happens. And the leap is too big to make in one step. But you could take another tack, which is to say that if determinism really doesn't exist, it must be possible to talk about the physics that's under your feet right now in a way that doesn't make such heavy use of that idea, because it's not really there. So there has to be some way of talking about Newton's laws that doesn't hardwire in determinism. It doesn't look deterministic, even though determinism emerges as some feature of the way it works, because it's, after all, just a way of rewriting the laws that you have. Is there such a way of talking about classical physics? There sure is. It's the principle of least action. And when we all learn about it in college or whenever it is we learn about it, if you're a European in junior high school or whenever it is, right? It's very startling. It's very startling. It looks like the particle is sniffing out every path it can take from A to B and choosing the one that minimizes the action. It turns out, for the kinds of actions we allow, the sorts of variations we allow, it's just a rewriting of Newton's laws. But it's a totally different philosophical starting point. And it bothered the people who discovered it that there was this radically different way of thinking about Newton's laws. And today we know why it exists. It exists because the world is quantum mechanical. And the classical limit doesn't land you on Newton's laws. It lands you on the principle of least action. So that's why it's always worth, people like Dirac and Feynman emphasize this a lot, it's always worth rewriting the laws that you have already. Forget about speculating about what comes next. It's worth rewriting the laws you have already in as many different ways as you can, because it's likely that the way that's been handed down to historically is not the way that's going to make contact with the next level of description. And so doing that with classical mechanics indeed did lead to the principle of least action, which was one step removed from quantum mechanics. That was the place to go to make the jump to the next level. Today we don't have the ghost of theorist future, but we have all these thought experiments that tell us that space-time has got to go, quantum mechanics maybe needs to be extended. And so what we can do is try to do the same thing. Try to rewrite good old-fashioned standard quantum field theory in a way where locality and unitarity, space-time and quantum mechanics, in the usual formalism don't play the same starring role that they normally do. So that's a grand motivation. The nice thing is that there's also very pragmatic reasons to suspect that this is possible, which is you look at what actually happens when you try to do the calculations with the standard procedure and the standard formalism. And indeed, even if we do these very simple things of perturbative scattering amplitudes, you find this famous fact. If you go to any of the talks in this workshop, this will be in one of the first or second transparencies. I won't go through it in detail. But if you even compute the very simplest processes, 2 gluons in, 2 gluons out, that's something that you can give on a problem set. And dedicated enough grad students can solve it. Already 2 gluons in, 3 gluons out. It's 30 dense pages of algebra. 2 gluons in, 4 gluons out is 80 dense pages of algebra. Completely ridiculous. It doesn't look remotely like it's tractable. And it looks complicated. Of course, you might think it looks complicated because it is complicated. Not every question has a simple answer. And part of the art of theoretical physics is declaring as interesting only the questions that have simple answers, right? So you say this is not a very interesting question. So big deal. It's complicated, right? But the astonishing thing is that the people who actually did these calculations because they had to for pragmatic reasons discovered that the results were amazingly simple in the end, that these 80 pages of algebra collapsed to a single term. Or collapsed to 3 terms. I mean, something astonishingly simple. So why is this happening? So this is already some indication there's something terribly wrong with the usual way of doing things. It's tremendously obscuring the simplicity in the final answer. And since then, we've discovered not only is it simple, 100,000 terms turn into 3 terms, but the answer has symmetries that are invisible in the usual formalism. So not only is it simple, it has symmetries, it has everything that's awakening you to the idea that there must be some that these amplitudes must be the answer to a different question. There must be a different formalism that computes them. And you can ask, why is it so complicated? Why do Feynman diagrams make it so complicated? And it's not some technical reason. It's precisely because the purpose of Feynman diagrams is to make locality and unitary as manifest as possible. And that's done with the very words that go into describing these theories, engaged theories, by introducing a humongous amount of unphysical redundancy into our description of the physics. And it's that humongous amount of unphysical redundancy which is being dragged around these calculations, ballooning into this factorial growth of number of terms in the intermediate steps that cancel out in the final answer. So we have two things. We have these highfalutin things telling us to try to abandon locality and unitarity as central principles in the way we think about physics. And we have this very practical reasons that say when we do make them central in our way of doing physics, we get horrendously complicated intermediate steps when the final answer is extremely simple. All right, so those are the reasons why it is worth trying to find a new formulation of this physics that's really just sitting under our feet. It's nothing exotic, but we're trying to do something with it. We want to eviscerate the usual central role of space-time and unitary evolution in our thinking. All right, so that's our goal for today. And for today, we will accomplish this goal. We'll accomplish this goal for a very limited, very baby theory, not the most general quantum field theory in the world, but the very simplest theory where you can make a start. And so we'll have it. So you'll see by the end of the lecture what such principles can look like, what the ideas can look like. But even without this concrete example, what should be very obvious to you, especially if you're a mathematician, is whatever these new principles are, if they exist, they must involve some very new mathematical structures. I mean, you're not going to get all of this incredible intricacy of the actual amplitudes for, in the end, remarkably complex and interesting functions of external kinematic variables we'll talk about in a second, which we normally get by thinking about path integrals and gauge symmetries and all this wonderful stuff. If we're going to throw all of that out and get it from some other starting point, there has to be some real juice and beef there to accomplish it. So that's why there's bound to be some very interesting new mathematical structures involved in this way of thinking about things, and we'll see one concrete example today. And the reason for the name will become a little apparent later. All right, so much for philosophy. Now I want to spend a little bit of time just telling you about more concretely what we're talking about. So we're talking about the scattering amplitudes of particles like gluons. Okay? So imagine a picture of a bunch of gluons in, a bunch of gluons out. So we can actually imagine equivalently that there's a vacuum and a bunch of gluons out. Okay? So just by switching the signs of the energies of the particles. So by convention, each one of the particles has a 4 momentum p mu, and momentum conservation is a statement that the momenta all add up to 0. Okay? Now, gluons or photons are massless particles. And so that means that these momenta, which have an energy component and a time component, are actually constrained. Okay, such that p0 squared minus p squared is equal to 0. So there's obviously only 3 independent degrees of freedom in specifying one of these null vectors. And there's one other piece of data. These particles have spin. They actually can be thought of having a helicity, to the spin of plus or minus 1 in the direction of motion. So the helicity is plus or minus 1. And so the amplitude, most primitively for gluons, is a function of giving the momenta of the particles and these helicities, which can be plus or minus 1. So there's 2 to the n different amplitudes we could be talking about if we have n gluons. OK? All right. Now, when we compute these things using Feynman diagrams, there's various levels of approximation. There's a lowest level of approximation which dominates the amplitude for n particles, which is that we draw all possible Feynman diagrams that can contribute to this process which don't have any internal loops. So if we have 5 particles, we might have diagrams like that. We can have diagrams like this. And sorry, that's 6. So I didn't draw a new one. All right, anyway. Okay? and so on. So we can have lots and lots of diagrams, so we can draw these tree-like diagrams. Okay? So that's what we have at the lowest order of approximation. At the next order of approximation, we can have diagrams that have internal loops in them, like so, and so on. Okay? And also, for some reasons that I won't explain in detail, there's a simplest possible limit of this physics where the only diagrams that contribute are planar. So we only look at, this corresponds to a well-defined limit of the underlying theory. But anyway, we only draw Feynman diagrams that don't have crossings. And we're only drawing planar diagrams. Okay? Yeah.
How much of this goes beyond planar?
For what I'm saying today, nothing. But it's all planar. But I'll have some things. I mean, if you're interested later, I can tell you at least some thoughts about what might go beyond the planar limit. So aspects of this, there's many aspects of this story. The final part, the actual amplituhedron, we only understand what it means for n equals 4 super Yang-Mills and the planar limit. But the sort of cousins along the way are much more general, and I can tell you reasons why we suspect it might actually go beyond that. OK. All right. So now, in the end of the day, then let's say we're only looking at tree amplitudes. Oh, so sorry. In these diagrams have now that they have internal loops. When they're tree-like diagrams, every momentum in this diagram is determined by momentum conservation. So that internal momentum is just the sum of those two momenta, and so on. When we have loops, there are undetermined momenta in there, and Feynman instructs us to integrate over them. So to get the actual amplitude, we have to then integrate over these things. But for the rest of the talk, I'm actually going to concentrate on the structure of the integrand before you carry out the integration. This is what you would literally get from summing the Feynman diagrams before you do the integrals. And it turns out that for planar diagrams, this is a well-defined idea. So at tree level, we just have an amplitude that's a function of p in the helicity. At loop level, we have a function of p in the helicity. And if I have L loops, I have L loop momentum variables. So there's a total of 4L variables here. Okay? The L's aren't constrained to be null. They're just totally random generic momenta. So this is a rational function, could be very complicated rational function of the momenta and the loop momenta, the external momenta, the loop momenta, depends on these 2 to the n different helicities. OK.
This is an organizational principle that you have in mind?
Sorry?
This is organizing them in H-bar?
It's actually organized in the underlying theory. So there's an SUN gauge theory here. I'm suppressing some, I'm suppressing a few things. But in the underlying SUN gauge theory, it's an expansion in powers of 1 over n. So you take the limit as n goes to infinity with g squared times n fixed, where g is a coupling. In that limit, as Tufte showed in the 70s, the only diagrams that survive are the planar diagrams. And so we're just looking at that. Note also, because all the diagrams are planar, it makes sense to label the external particles in a cyclic ordering. Okay? So this object, modulo the choice of what the helicities are, it has a natural cyclic structure. The p's are ordered, p1, p2, p3, because the external labels are ordered and the diagrams are planar.
How does physics emerge or doesn't emerge from this?
Sorry?
How do instantons bias or unbiased?
Very good, yes. So in this large n limit, there's no instanton corrections. The instanton corrections are actually 0 in this limit. Because the instanton corrections actually go like e to the minus 1 over g squared.
What happens if you ignore the fact that you could have also an entropy in the vacuum?
No. In the large n limit, this really does not happen. So it's because of this. So the instanton effects go like e to the minus g squared, which is e to the minus n over this thing that you're keeping fixed. This is the Tufte coupling.
We have many of them.
Yes.
They fluctuate.
It doesn't matter.
There could be a density in front of them that could.
Well, we could go into this later, but in this large n limit, it actually does not happen. And it's actually well known in the theories that we're talking about. We even know what the large n limit does. We know what it does at weak coupling, we know what it does at strong coupling, and it's smooth. There's nothing, the perturbation theory is a finite radius of convergence. This is a generic feature of going to large n. So there's a lot of simplifications that are happening in this limit. But anyway, I don't care about these non-perturbative corrections at the moment anyway. I'm going to have my hands full with the perturbation theory. All right, now, I just want to spend a few minutes telling you how are these 2 principles of unitarity and locality encoded in this answer. Okay? In other words, one way of guaranteeing that the answer is consistent with relativity and quantum mechanics, locality and unitarity, is to do the calculation using Feynman diagrams. That's their purpose in life, to make that manifest. But let's say someone told you, trust me, I've done the calculations. This is the answer. And they just hand you the final answer. How would you know that the result is compatible with locality and unitarity? It's very simple. Locality and unitarity are encoded in a very simple property of this rational function. And I'll tell you what that property is. And this is all a little loose for now. I just want you to see some pictures and some patterns, and so that when we switch to talking about the mathematical object and everything that I'll tell you is very sharp, you'll at least see how properties of that mathematical object are literally giving us these principles, or these consequences. OK, so one thing which is totally obvious from drawing Feynman diagrams, okay, is, let's say even at tree level, is that these rational functions have a very special kind of pole. Okay? They don't have arbitrary pole structure. In fact, all of these, the only singularities come from these propagator factors. These propagator factors, Feynman tells us, is always some 1 over p squared, where p is the momentum flowing through that line. And so we learn that the only kind of singularities that we can have in a Feynman diagram look like 1 over p squared, where p is a sum of consecutive momenta. It's consecutive only because of the ordering of the external particles. Okay? So whatever I do, however many lines going in the end, the only kind of pole I have is when one of these internal lines is going on shell. So in an old-fashioned language, we say those are, or in a standard language, we'd say those are virtual particles, and the singularities arise when the virtual particles become real. Okay? This is locality. The fact that these are the only kinds of poles, and you don't have more complicated poles. If I hand you a random rational function, it could have poles that look like 1 over p squared q squared minus r squared t squared. It could have much more complicated poles. If it has poles of that sort, it's the wrong answer. It's not local. Locality is encoded in the amplitude in the statement that the only poles have this very special structure that look like 1 over p squared. Okay, so that's locality. And unitarity, which is that this is consistently interpreted as a quantum mechanical process, is that on this pole, the amplitude factorizes. The residue has a very specific property, right? So if I have an endpoint amplitude on one of these poles, on this pole, it's not just randomly that the pole develops. It develops because there's some internal particle that's going on shell. Because it's going on shell, it means that I can interpret it as this physical process happening with a massless intermediate particle there, and then going out and having the rest of the process happen on the other side. Okay? So, yeah. Sorry?
Higher derivative theory, is that local according to you?
Yes. Yes. And higher derivative theory, you see, I'm talking about the. Sorry?
Yeah, no, any.
Oh no. Sorry. I will no. So higher derivative theories in the sense that you imagine, I will only ever think about the higher dimension operators as insertions. I will never put them in the propagator. Okay. So if you treat the higher dimension operators as local insertions, then it's local. If you do the thing that you did, it's illegal, and I will not allow it. So I only allow 1 over p squared poles. But anyway, I'm only dealing with the standard normal. Everything is very vanilla. Okay. So this is localities where the poles are, and unitarity is that on the poles the residues factorize in this particular way. All right. Now, in fact, if I hand you some rational functions that have this property, you would think, where could it possibly come from, other than a picture where you sum over all possible diagrams with these things arising from particles going on shell in between, right? Again, that's the purpose in life of the Feynman diagrams, to make that manifest. There's a very similar statement at loop level, but maybe for the purposes of this talk, I will stick with talking about mostly things at trees, and then I will later tell you, if I have time, what the interpretation of loops is. All right. OK. So that very simple, this kind of pole and this kind of factorization is locality and unitarity at tree level. Now, a very powerful idea that really goes back to the 60s, but was brought to full fruition only in the last decade, is that we can exploit locality and unitarity to determine the amplitude recursively. And the idea here is, roughly speaking, we know what all the poles of the amplitude are. So we should be able to use Cauchy's theorem to reconstruct the full amplitude from the knowledge of where its poles are. Okay? And in practice, this is done in a very simple way. You take the amplitude and you just take two of the momenta and you deform them to make them complex. You can't just deform one of them because momentum has got to be conserved. So you add something to one, you subtract something from another one, and then you look at what the analytic structure of the resulting function of the complex plane. We know where all the poles are. We know how they factorize. We know what the residues are. And there's, for somewhat magical reasons, there's no pole at infinity, so there's no unknown contribution. And so you can reconstruct the object purely from knowing what its poles are. And that means, quite remarkably, so these were known as the Brito, Cacciazzo, Feng, and Witten recursion relations. So it gave you a way of determining, 7-point tree amplitude in terms of 6-point tree amplitudes, 5-point tree amplitudes. And you keep going all the way down to the thing that you can't decompose any further. And for reasons I won't have time to go into, there's two basic kinds of 3-particle amplitude. Okay? These two basic kinds of the reason there are two of them is, remember, these gluons have helicity. So the helicities can be plus, plus, or minus or plus. For good reasons, the all plus and all minus aren't interesting. So we only have plus, plus, minus, or minus, minus, plus. So these are the two basic kinds of 3-point amplitude. And so we can reduce recursively. We can reduce the tree amplitudes all the way down to these basic building blocks. One of the remarkable features of this recursion is that there's a way of actually representing what the amplitude is directly. See, when you calculate Feynman diagrams, you have a picture, for example, that looks like this, or maybe a picture that looks like that. And we have these words like, that's a virtual particle, that's a virtual particle. This idea of virtual particles permeates all of our, all the linguistics of discussions in quantum field theory. But these are really objects that are in our head. This is, part of the formalism. It's not necessarily part of the physics. And indeed, there's a way of talking. This recursive way of constructing things gives you a completely different set of words, where the notion of virtual particles never makes an appearance. Okay? In fact, you can take these elementary 3-particle amplitudes. Every particle here is massless. And there's a canonical way of gluing them together. Not as virtual particles, but everything as real particles. So for example, I can draw a picture like this. Every particle in here is on shell, is a massless particle. But the momenta, there's still some momenta undetermined. So you integrate over all the possible massless particles, all the possible on-shell massless momenta on the inside compatible with the momenta on the outside. Okay? So this is a well-defined operation. You can take these elementary black and white vertices and glue them together in arbitrarily complicated ways. You can, this one isn't arbitrarily complicated, but this is another simple thing that you can draw. You can draw all sorts of pictures like this with black and white vertices. And they have a nice interpretation. They are direct on-shell physical processes, no virtual particles involved. And what's remarkable is that the tree amplitudes are actually represented in this way. That's the 4-particle tree amplitude. There's no virtual particles in this picture anywhere. But if you compute it, and if you compute it using recursion relations, that's how it comes out. It comes out as just that picture. That's the 5-particle tree amplitude. See, it looks like it has loops in here, but it's not. These aren't Feynman diagrams. Okay? These are a different kind of diagram. Call them on-shell diagrams or twister diagrams. They have all sorts of names. So this is a way of writing the amplitudes directly in terms. So there's a new physical idea. There's no virtual particles. You can represent amplitudes directly in terms of those on-shell processes. And of course, there's no, there isn't a complete free lunch. Here we have a picture that looks like a tree, but with a virtual particle. Instead of having a tree, we have 2 on-shell particles here, right? So we're trading. We add more and more intermediate on-shell particles to mimic the effects of the virtual particles. But from this picture, we never say the word mimic. We've never heard about this. This is the way of building up the answer from this point of view. All right. Now, one interesting thing that happens is you discover, so in these examples, there's only one diagram. Typically, these recursion relations give you, for example, if we go to 6 points, at 6 points, you get a sum of 3 diagrams. And each one of the diagrams is one of these little black-white dot pictures. Okay? Because it's a recursion relation, you can do the recursion in many different ways, and you get lots of different representations of exactly the same object. It doesn't come out in a unique preferred form. You can do it in lots and lots of different ways. So that's interesting. And finally, something that's, so it's extremely simple, I should say. So you do the 6-point calculation like this. You get 3 terms. You do Feynman diagrams. You have 30,000 terms or whatever it is. So it's vastly simpler. Remarkably, if you look at any one of these building blocks, you cannot interpret it in a way that's local. Any one of the building blocks does not have poles that looks like that. Any one of the building blocks has some poles that look like that and some of the illegal poles that we talked about. So the extreme simplicity is coming at a cost. The building blocks aren't local. They clearly don't care about space-time. They're coming from somewhere else. Okay? But something miraculous happens when you add them all up together. All these spurious non-local poles cancel, and you're just left with something with physical poles. Okay? So the enormous simplicity of the answer is coming as a consequence of liberating yourself from locality at the level of the building block. So that's one interesting thing. And another interesting thing that was observationally discovered is that each one of these terms by itself has all these infinite dimensional symmetries of the theory that I mentioned before, which I haven't explained to you what they are. But there's an infinite dimensional Yangian symmetry that these scattering amplitudes have, totally invisible in Feynman diagrams, but not only visible, but visible term by term in this on-shell way of organizing it. Okay?
1/n. So unitarity usually is a statement about the cross-section in
Yes.
the imaginary part.
Yes, yes.
And now, because you organized it in 1/n, you have reshuffled things into 3 and loops.
I told you what the I told you what the if you I cut to the chase and told you what the statement of unitarity turns into here. The statement of unitarity, even at tree level, is literally the statement of this factorization and what the residue on that pole looks like. And if you go to loop level, there's a cousin of that statement, which I did not say. I can tell you later. But let's just focus on, just for time's sake, let's focus on the tree level part for the moment. Yeah.
Organize in 1/n.
Yes. No. Well,
In theory, you are saying this is also true?
Yes, absolutely. Yes. In fact, at tree level, the statement about unitarity at tree level is the very simple statement of where Feynman instructs you to put the I epsilon in the propagators. Anyway, that statement is literally the statement S dagger S equals 1. I mean, literally, that statement already is meaningful at tree level, and it gives you the statement that I just told you. I'll be very, the story at loop level is actually fascinating and is very natural. Well, I'll tell you what the mathematical part of the story is, and I'll just have to assert that it turns into loops physically. All right. So where have we gotten so far? We've seen that locality and unitarity are some very sharp statement about the singularity structure and the factorization of amplitudes. Some interesting rational functions. True at tree level. There's a related statement at loop level. We've seen that we can exploit locality and unitarity to build the amplitude in a very different way than Feynman diagrams. The physical guiding principle is no virtual particles. Everything is on shell all the time. And there is a benefit to doing things that way. You see all the symmetries in your face. And you reduce everything down to these elementary building blocks, these 3-particle amplitudes. Remarkably, the building blocks aren't local. The building blocks don't have a space-time description. But somehow they sum together in a nice way. And the collection of them, which is determined by being local and unitary, gives you the amplitude. All right. And just to give you a concrete example, maybe there's just two more little bits of notation, and then we'll get into the amplituhedron proper. So first of all, remember that we had these amplitudes that were functions of momenta and helicities. These helicities were plus or minus 1. Now, these momenta, remember, there's 3 independent variables here, right? So this is somewhere you'll have to trust me, but we're going to trade these 3 variables in the P, which is really a 4-dimensional vector, but it's 3 variables because of that constraint. We're going to trade these variables for another 3 variables that I'll call, use consistent notation, ZA. These Z's are 4-dimensional vectors. So this Z is a 4-dimensional vector, but up to a rescaling. Okay? So these Z's live in P3. Right? So the 3 degrees of freedom for every external massless particle is replaced by a four-dimensional vector up to rescaling. And in fact, the SL4 symmetry, there's a natural SL4 symmetry that acts on the z's, is actually the conformal symmetry of the space-time theory. Okay? In fact, the Lorentz symmetry is SL2 cross SL2, which embeds in the SL4 in an obvious way. But the whole theory is a theory of massless particles. It has conformal symmetry. And the action of that conformal symmetry is as nice as possible. It just acts as 4x4 linear transformations on these projective variables z. These are Penrose's twistor variables, which in this story are purely kinematical things. They're extremely useful to keep track of the kinematics in as simple a way as possible. They have no dynamical content. We'll get to where the dynamics comes from. Okay? Now, one more thing. So in these variables, I have to tell you what do these poles correspond to? Remember I told you that the amplitude needs to factorize in this way when there's an I plus 1, j plus 1. Okay? That's when the sum of all the p's between I and j becomes null. Now, what does that mean in terms of these z variables? Well, there's only one thing it could mean. These are points in a projective space. So the only special thing that can involve these 4 points, zi, zi plus 1, zj, zj plus 1, is that those 4 points in P3 become coplanar. Okay? So if those 4 points become coplanar, so we have this, so the amplitude, it's a function of the p's and these helicities. Now I'm telling you that this is really better thought of as a function of the z's and the helicities for the moment. And this singularity is just when zi plus 1, zj plus 1 become coplanar. Or I will often draw a bracket like this. Every time I put any number of objects in a bracket, I mean you take the determinant of those guys, or you contract them with the totally antisymmetric tensor according to a taste. Okay? So it's when zi plus 1, zj plus 1 goes to 0. These are the only SL4 invariant objects that I can build. It's when that goes to 0 that this thing is supposed to develop a pole. Okay? And on that pole, it's supposed to factorize into this picture. Now, who could that intermediate line be? Well, if I plus 1 and jj plus 1 are coplanar, then those two lines, I plus 1 and jj plus 1, intersect at a point I. Okay? And that point I is that little point I which appears in that picture. Okay? So we have a function of these projective variables z, and it has to have poles only when these 4 brackets go to 0. And on those poles, it needs to factorize in this way. All right? So that's what locality and unitarity mean. And a final technical point I'll just mention quickly is that instead of dealing with these ugly 2 to the n different variables for the helicities equals plus or minus 1, it's very useful to think about a maximally supersymmetric version of this theory. And from our point of view here, the supersymmetry is, I mean, it plays many roles later, but at this point, it's just a very convenient bookkeeping device. Because instead of talking about one particle of helicity 1 and one particle of helicity minus 1, and they're sort of disjoint from each other, we fill it in between with particles of helicity half, 0, minus a half, and minus 1. There's 1 of these, 4 of these, 6 of these, 4 of these, and 1 of those. And there are symmetries that allow you to rotate this guy into that guy, into that guy, into that guy, and that guy. So you embed all of these guys in one multiplet with each other. Okay? So instead of having them be disjoint, they're actually all unified into one nice multiplet. And because of that, it's not natural to label the states with these plus or minus 1 variables. But because the theory is supersymmetric, you shouldn't be surprised that it's natural to label it with a certain Grassmann variables, 4 Grassmann variables that go from 1 to 4. So instead of the helicities, what plays the role of helicity is now we have a function that depends on some super twistors ZA. And these ZA are nothing other than, well, there's the bosonic part, which are just the Z's that we talked about, those 4-dimensional guys up to rescaling. And there's some Grassmann variables where there are 4 of them as well. All right. And the final variable that I'll talk about is one more grading of this, which is a variable k. since these are odd variables, any function of these z's is a polynomial in the etas. And so we can organize this polynomial by the number of etas that it has. So it can have terms with no etas, 4 etas, 8 etas. It comes in multiples of 4 because there's a SL4 symmetry acting on that index, much as there is on this guy. And so MNK is that part of this big underlying superamplitude that has precisely 4k etas in it. All right. So anyway, so that's so I mentioned this because we're going to be seeing n and k again a lot. And in fact, if we do this decomposition a little more carefully, what turns out is that if we look at m and n and k, then if ii plus 1, jj plus 1 goes to 0, then we have to have these two factors. There's actually another little factor here that tells us exactly where ii plus 1, jj plus 1 are on this plane altogether. And what's left over has some k left and some k right here, with k left plus k right equals to k minus 1. All right, so now I've told you everything I want to tell you about the kinematics of how to describe these particles, the amplitudes, the variables, what locality and unitarity look like. So I want you to remember this ii plus 1, jj plus 1 structure. That's locality. And the fact that things break up into pieces as you approach those poles is unitarity. Okay. Once again, Feynman diagrams make this obvious. But we're now going to talk about a structure where none of these words appear, where all of this is going to come out from a totally different starting point. But of course, the structure is going to tell us more things as well. All right. So again, literally for what I'm talking about, for the final thing that I'm talking about, critical. Okay. But what I'm talking about today is a sort of last step of a number of things that came before it. And as we go further back in time, it's less and less important. So we can maybe talk about the speculations later about how the object that I'm talking about will deform beyond supersymmetry. But at the moment, let's just say absolutely critical. Okay, so what I'll focus on is just n equals 4 super Yang-Mills in the planar limit unapologetically. And if we manage to accomplish something beyond that later, then I'll be happy to come back and give another talk about it. Okay. Okay. Of course, I suspect we will. Otherwise, I wouldn't spend so much of my life on this problem. But I don't really care about n equals 4 super Yang-Mills. But the idea is to try to do this for the simplest possible theory, where if there is going to be any structure, we're going to see it. And so I think we're starting to see a structure. So now it's an open question whether it's an accident or whether it's going to extend. All right. Now, just so you have a concrete example, let's look at this 6-particle amplitude. Okay, the 6-particle amplitude, I told you, is a sum of 3 terms. And I want to show you one representation for what those 3 terms look like. And I will define what I'm talking about in a second. Okay, so it's a sum of 3 terms. They depend on these funny 5-bracket objects. So let me define what you're not going to need to know this in detail, but just so you see, there's some very explicit formula here. This is, so remember, it's some polynomial in the etas. So that's that particular polynomial in the etas, and its dependence on the rest of the bosonic variables. It has the following poles. Oops. Has 5 poles downstairs. So remember, these brackets are just the determinants of these 4-dimensional bosonic z's. That's a very concrete rational function. It's a function of the etas. It's a function of the z's. All right. And if you add up these 3 special terms, you get the 6-particle amplitude. Now, if you just want the 5-particle amplitude, it's just that guy, 1, 2, 3, 4, 5. What could be nicer? Now, let's look at that guy. That guy's perfect. It has everything it should. Its poles are 1, 2, 3, 4, 2, 3, 4, 5. So all of its poles are these ii plus 1, jj plus 1 poles. They're all the physical poles, exactly as we expect. It's correct. That's great. It's just one term. That's wonderful. But let's now already go to 6 points. And you see already at 6 points, this is a disaster. For example, if I look at now 1, 2, 3, 4, 5, this pole 5, 1, 2, 3 is no longer of the form ii plus 1, jj plus 1. The 6 is stuck between 5 and 1. Right? So that pole is a non-local pole. It's a spurious pole. In fact, typically, each one of these terms has 4 non-local poles and 1 local one, 1 good one. 4 bad ones and 1 good one. So any given one term is meaningless. It doesn't have a local space-time interpretation. The sum is the full amplitude. On the other hand, each one of these terms is associated with one of those beautiful black-white dot pictures. Each one of these is one of the building blocks that represents an on-shell process. So it shows you very concretely that each term has a nice life of its own. Each term manifests all the symmetries of the theory. But each term by itself isn't local. You have to glue them together in a very particular way to get the right answer. And if no one told you, if someone just handed you these objects and said, play with them, you would never guess that you should put them together in this way. Your desire to put them together in this way is because you want to make the answer local and unitary, because you're a physicist and you've heard that this is a good thing. Right? But it's not the answer to a natural mathematical question. Even though, as we'll see in a second, each term by itself is associated with a very natural mathematical object. Right? In fact, if I tell you what the answer turns out to be for general n, the answer for general n is the sum over n of 1. This is all for k equals 1. It's of these particular 5 brackets. 1 I plus 1 jj plus 1. So you see what a sort of weird object this is. There's a 1 sitting there, right? 1 is special. That's crazy. This object is cyclically invariant, right? Doesn't look cyclically invariant, but there's some miraculous identities that these guys satisfy that make the result cyclically invariant nonetheless. Each term has 1 pole that looks right. One of these 4 poles downstairs is I plus 1 jj plus 1. But 4 of them look wrong. And again, somehow remarkably in the sum, they all turn out to be right. So what would ever make you take these funny 5-term objects? What would make you put them together in this way, other than your desire to make it local and unitary? This is an example of the question, the sort of question that we didn't know the answer to 6 or 7 months ago that we now know the answer to, that the amplituhedron is the answer to. Okay? All right. So that's it for the physics motivation. As I said, that took longer than I anticipated. But now let me turn to telling you what the mathematical structure is. Okay? So now forget about all the physics. And we're going to do 2 things. We're going to start with triangles. And we're going to have one generalization of triangles, which leads to the idea of the positive Grassmannian. So this is already an interesting story and is related to scattering amplitudes in a way that I'll make clear. So I'll spend a little bit of time talking about that. But then there's another generalization of triangles to polygons. Polygons generalize into the Grassmannian. So you try to generalize this into the Grassmannian, and you get the positive Grassmannian. If you generalize the notion of a polygon into the Grassmannian, you get the amplituhedron. And if I say what the vague thing is that we're looking for, you see, in this example, it looks like we have all sorts of building blocks. There are nice building blocks. We're putting them together in a very special way. But we don't know why we're putting them together in that particular way, other than the desire to agree with what we expect from physics. So what other question could they be the answer to more naturally? And we had this sort of vague fantasy for a long time that the amplitudes are somehow the volume of some region in some space. And to compute it, you have to triangulate that region somehow. And there's no unique way of triangulating it. There's lots of ways of triangulating it. And each triangle, each piece is one of those terms. And if we knew what the object was that we're triangulating, that would be great, because that would be the invariant definition of what it is. And the amplitude would just be its volume, full stop. And that's something we're looking for a long time, but there's lots of obstructions anyway. That's what we now know. Okay? And as we'll see, the big object that we're triangulating is the amplituhedron. The big object is the amplituhedron. The little building blocks that it's made out of are cells of the positive Grassmannian. And after I describe that analogy, I think this statement will become clear. All right. Oh, I could be using these. All right, so let's start doing it. So let's first talk about a triangle. So I really mean a triangle. So just 3 points in two-dimensional Euclidean space. Because I'm a physicist, I'll even discuss you by putting vector signs over them. Okay, so they're really points in a two-dimensional Euclidean space. And now, given those points, I would like to know what are all the points that are on the inside of the triangle. Right? Well, this is all very trivial, so I'm going to spend a long time on this trivial example, but emphasizing the things that are going to generalize nicely. So how do I talk about a point on the inside of the triangle? Well, a natural idea is to imagine these points have masses, which I'll call C1, C2, and C3, and to look at the center of mass of all the points. So C1, Z1, plus C2, Z2, plus C3, Z3, over C1 plus C2 plus C3. And so if these C's are positive, then I land inside the triangle. And if I arrange over all the possible C's, I cover the entire inside of the triangle. Okay? Right. Now, this is obviously a projective notion. I can rescale the C's, and I get exactly the same point. And so it's, in fact, very convenient to say this whole thing more nicely projectively. Instead of talking about the two-dimensional vectors, I'll talk about a three-dimensional vector z up to rescaling. So my coordinates are z1, z2, and z3. The coordinate of this internal point is y. And so I'm saying that y is of the form c1, z1, plus c2, z2, plus c3, z3. That's all, with all these CAs positive. So c1, c2, c3, which are only defined modulo GL1, with all the C's positive. OK, so that's the inside of a triangle. I give you a triplet of numbers mod GL1, positive numbers mod GL1, and that's it. Thus, arranging all of them gives me the notion of the inside of a triangle. That's a trivial notion. We can, of course, by the way, when I say, I really mean the ratios are positive, so I'm always going to, by convention, choose one of them to be positive, and everything else is a positive. So I won't keep saying that. I'll just say that they're all positive. OK, so now we can first generalize that to a simplex. So that's the obvious generalization. So we can have n numbers, C1 up to Cn mod GL1, with all the Ca positive. And that gives me the inside of a simplex, n-1 simplex. But now there's a slightly more interesting generalization of this, which is to, well, so we can also think about, think about these n numbers as giving me some vector in an n-dimensional space. Because I can rescale them by anything. In fact, it's not the vector that matters, but just the line that's determined that matters. So I have a line in an n-dimensional space. So associated with a line in an n-dimensional space, all the space of all lines in an n-dimensional space with this positivity constraint gives me the inside of a simplex. So I can now generalize that to not just lines in an n-dimensional space, but k-dimensional planes in an n-dimensional space. So I go from G1n now into GKn. So the Grassmannian is a space of k-planes in n dimensions. And if I say it back in this language, I now imagine k-dimensional vectors, which I'll annoy you again by putting vector signs on them. Okay? So I have n k-dimensional vectors mod GLK. So that's the vertical way of talking about this k by n matrix, just a configuration of n k-dimensional vectors modulo GLK. I can also think about that matrix horizontally as giving me k n-dimensional vectors whose span generates a k-plane in n dimensions. So that's the k-plane in n-dimension way of thinking about it. But anyway, either way, it's a configuration of vectors modulo GLK. And now what could the analog of positivity be? Obviously, it's not that each entry is positive. That's not invariant under GLK. The only statement that I can make is invariant under GLK is if I choose an ordering, I pick one ordering for the external, for the columns, 1 through n, and I demand that all the k by k minors of this matrix are positive in that ordering. Okay? So that's the generalization of the inside of a triangle into the Grassmannian. And that's known as the positive Grassmannian. So this is the object that's been studied in many different guises, of course, implicitly a lot in Lustig's work on positivity from many points of view, and Sasha Goncharov studied it from many points of view. Sasha Posnikov studied it in tremendous detail. So this is an object that mathematicians have been talking about for a number of years now, relatively recently in the last decade. All right, so this just generalizes the notion of an inside of a triangle into the Grassmannian. Okay? This k is the same k. This k is going to be the same k. So already you see the two integers are the same. There's n and k. All right? Right. The two letters are the same, not coincidentally. But I'll tell you what the connection is a little more in the moment. Remember, I told you to forget about the physics, right? We're just doing dumb, very fancy, deep mathematical things. Sorry. Dumb is meant as a compliment in this setting. Natural. By dumb, I mean natural things. Relatively natural things. Notice that this thing almost, you might think there's n factorial different positive parts of the Grassmannian for each ordering, but there aren't. Actually, there's only n minus 1 factorial different parts because it depends only on a cyclic ordering. Because if in a given ordering the minors are all positive, then if you shift C1 to C2, C2 to C3, and Cn to, and this, you do a little jig here, minus 1 to the k plus 1 C1, so it's a twisted cyclic symmetry. If the old minors are positive, the new minors are positive. So there's a twisted cyclic symmetry. Okay? That's just some emergent fact. So for a given cyclic ordering of the external parts, there is a natural associated positive part of the Grassmannian. This is a twisted cyclic symmetry. OK. Now, simplices are wonderful and pretty boring. And it's because going to the boundaries of simplices are just lower dimensional simplices. So these are very, very simple objects. The positive Grassmannian, by contrast, is much richer and much more interesting. And the reason is that these constraints aren't linear. Okay? And so if you want to go to the boundaries of the positive Grassmannian, you can't just willy-nilly set any minor that you like to 0. The minors satisfy relations between each other, and you can't just randomly set them to 0 to head to boundaries, like you can for a simplex. When there are just c's, c1 through cn, going to boundaries correspond to setting some of the c's to 0. They're forced to be positive, so the boundary is when you set them to 0, non-negative. But you can't do that randomly with these minors. Just to give you some feeling for what that constraint looks like, which will also be useful in a moment, let's try to visualize. The simplest thing to visualize would be G2n. But for my purposes, let's actually think about G3n. Okay? Let's think about G3n. And let me imagine that the c's as given have the property, I don't know, that the top component is positive for all of them, so that I can rescale it to 1 without changing the fact that the minors are positive. So let me look at a special set of vectors, 3-dimensional vectors. So I have a 3-by-n matrix which I've put in this form, okay? Just to get a feeling for what positivity means. So the data of this 3-by-n matrix is just giving these coordinates, C1 through Cn, again in a 2-dimensional space. Now, if I hand you these c's randomly, here's 1, 2, 3, 4, 5, 6, 7, 8, 9. This won't be positive. Obviously, you pick random things, the minors won't all be positive. What does it take for all the minors to be positive? You have to make a convex polygon out of the C1 through Cn. Right? So they have to have a convexity property. Right? It's clear, because these 3-by-3 minors are nothing other than the oriented areas of the triangle with coordinates Ci, Cj, Ck. So it's telling you that every triangle inside has the same sign. All the areas have the same sign, which tells you that the polygon is convex. But you see, this is pretty cool. If someone just handed you randomly a bunch of points and said, is this polygon convex? You don't have to go draw them to decide. You just compute all the minors. If they're all positive, it's convex. Okay? It's an algebraic statement that replaces that implements this condition of convexity. This also gives you a picture of why the boundaries are so interesting. See, if this is 1, 2, 3, 4, 5, 6, let's say I want to go to the boundary. So this is some generic configuration where all the minors are positive. Let's say I want to go to a boundary. And I think, well, the minors are all positive. So for example, 1, 3, 5 is positive. Let me just send the minor 1, 3, 5 to 0. Sending the minor 1, 3, 5 to 0 means making the points 1, 3, and 5 collinear with each other. But let me try to do it. Let me try to take the point 3 and move it to the line 1, 5. You see, I can't do it. Before it gets there, it's going That's going to happen. And if I keep it going past that point, it's no longer going to be convex. So I can't just willy-nilly set any minor that I want to 0. Okay? In fact, going to the boundaries of this guy, it's just the moduli space of convex polygons in this case, nothing else. And you see that even though I didn't say it, all I said in the beginning was that all the minors are positive, you start having to put conditions between consecutive points. First 3 consecutive points become collinear. Then past that point, many things can happen. Maybe the next point becomes collinear. Maybe 3 collides with 2, and so on. So you can degenerate these polygons more and more and more. Degenerating them more and more and more goes to lower and lower cells of the positive G3n. That's the analog of the faces of the simplex, but it's much more interesting now. Okay? And so there's some rich structure of this big object. I mean, you can loosely think of it as a polytope. It's not really a polytope because they're not linear equations. It's like a curvy thing living in the Grassmannian. But it's like a polytope. There's the inside, there's the first faces, there's edges, vertices, and so on. Right? There's a stratification of the space of n k-dimensional points where you put this additional cyclic structure in positivity. This beautifully stratifies the space, gives a notion of dimensionality, gives a cell decomposition. And that has all been wonderfully worked out by our mathematician friends. But that just gives you an idea for why the positive, even though I described it so trivially, this is just the object. It's very rich as a. Now I'm going to just make some declarations. This is not meant to be obvious, but it turns out to be true, and it's the sort of halfway point to discovering what the whole structure of the amplituhedron is. And this is also what was done together with Goncharov and Pasnikov and the rest of our friends back in December. So, claim. The cells of the positive Grassmannian are labeled, the cells of GKN are labeled, first of all, by a certain permutation. An affine permutation. So what I mean by this is if you take 1, 2, 3, 4, 5, 6 goes to 3, 4, 1, 5, 6. What happened to 2? 2. Okay. Then that's a certain permutation. An affine permutation means whenever you see something like this, if you go forward, it's OK. But if you jump back, you should add n. If you have 6 points, you add 6. So 1 to 3 is OK. 2 to 4 is OK. 3 to 1 is really 3 to 7. So your place is 3, 4, 7, 5, 6. 6 goes to 2, 8. OK? So that's all. So you just add n whenever it jumps backwards. So the data is n, the number of particles, the permutation, the number of particles, and the number of them that jump back. K is the number that jump back, or the number that go up above. Anyway, so just what I said. So for n and a k, there's a notion of an affine permutation. For each one of these affine permutations, there's a cell of the positive Grassmannian. Okay, so A. B, that cell of the positive Grassmannian, it can also be represented by certain diagrams. And this is a generalization of a picture very familiar to both physicists and mathematicians of representing scattering processes in 1 + 1 dimensions via permutations, again, in the story that's very familiar from the Yang-Baxter relation, and so on. Okay, so, but instead of drawing a picture where you represent the permutation just by drawing arrows for where everybody goes, which is a very familiar way of representing a permutation, which you can also interpret as a scattering process in 1 + 1 dimensions, there's another way of representing permutations that's more interesting, and which can be represented as a scattering process in 3 + 1 dimensions. Okay? Actually, the 3 doesn't actually matter, but I'll just tell you what the answer is. So the answer is that if you take exactly one of these pictures, okay, that a picture like this represents an affine permutation and also represents the corresponding cell in the positive Grassmannian. How does it represent an affine permutation? Well, we order the points on the boundary of the disk, And to read off the permutation from the picture, you walk into the graph. If you hit a white vertex, you make a left turn. If you hit a black vertex, you make a right turn. Okay? And that gives you a certain permutation, okay, which you can read off from the graph. So the invariant backbone is a permutation. It's associated with the cell of the positive Grassmannian in an interesting way. Those cells can also be represented graphically like this. There are elementary moves on these graphs that actually leave the permutation invariant. So there's a whole equivalence class of graphs that represents the same cell. And now these pictures should strike you as familiar from our on-shell picture for computing scattering amplitudes in the earlier part of the talk. In fact, they're identical. Okay? And those equivalences which preserve the permutation are exactly equivalences that preserve that answer, that physical answer. So this is not an obvious statement, but there is a complete bijection between this way of building scattering amplitudes as on-shell processes and associating each one of those building blocks, each one of the pieces, with a given cell of the positive Grassmannian. Okay? Now, I haven't told you some things. Yes? Right. Yeah, that's right, exactly. It has formulas associated with it, exactly. So here there's no formulas. The final thing has formulas. Okay? And so there's a dictionary for how to convert the thing without formulas to the thing with formulas. Okay? And actually, because it'll be easier for me to write down the sort of final answer for what the full object is, let me defer telling you what that dictionary is for a second. I'll tell it to you in the end, rather than at this intermediate point. But just trust me for the moment that there's a totally well-defined. In fact, this is one way of discovering this whole structure. Had the mathematicians not existed, but we were really interested in computing these on-shell diagrams, and we really pursued actually computing them. If you just begin responsibly calculating these diagrams, you find it's difficult to do the computation in the most obvious way, in the way the three-point functions are normally handed to you. But if you think a little bit more about a more natural way of representing the three-point functions, the Grassmannian comes into life. And once you represent them the three-point functions in that more natural way, the act of computing this physics process builds for you the cell in the Grassmannian. So the physics tells you what to do at every step. In fact, there are some combinatorial aspects of this problem which were non-trivial to work out from the purely combinatorial point of view that the physics point of view actually almost trivialized. So there's a better way of thinking about even organizing the combinatorics, which is much more natural to a physicist. Not so obvious combinatorially, but actually makes the combinatorics easier. So it's not historically how it happened, but doing this physics computation would actually build the whole connection with the Grassmannian very naturally. It's not an out-of-the-blue thing at all. But you have to spend some time understanding how to represent the three-point amplitudes in the most natural way.
Is the symmetry group now
yes.
a permutation group?
No. The symmetry group is the Yangian of SL4/4. And I will tell you a little bit more where the Yangian comes from in a moment. But all I wanted to highlight here is that there's a picture where you're building the amplitudes as sums of cells of the Grassmannian. Take this cell, that cell, that cell, that cell, that cell, and you're throwing them all together with this dictionary to convert them to the actual amplitude. Right? So now the question becomes, why those cells? Why are you taking those cells and jamming them together? Right? And again, we're instructed to that way by these recursion relations because that's what it takes to make the answer local and unitary. But why? Is it an answer to another question? OK, so that's how far we got with generalizing triangles. So the triangle is generalized to the positive Grassmannian. OK, so next. So I'm heading towards that picture now. Now I want another generalization. Instead of 3 external points, let's say there's 4 or 5 or some other number, any number of external points. And now I want to talk about the notion of an inside of a polygon. An inside of a polygon with those as vertices, the z's as vertices. All right, so I mean, you would just naturally draw it like that. So, OK, we're done. But here there's something a little bit tacit, which is that, in fact, if I just give you the points 1, 2, 3, 4, 5, it's not obvious what the inside means canonically with those things as being vertices. After all, it could have looked like 1, 2, 3, 4, 5, 6, 7, like that again. Right? So let's say that's what it looked like. 1, 2, 3. I mean, of course, I can look at the convex hull of all those points, but then not every one of the z's would be a vertex of that region, for example. Okay? So there's no canonical notion of inside if I just hand you a bunch of random z's. If If I make the external data random, then there isn't a nice canonical notion of inside. But we know what we can do. We can put some constraint on the external data, on these z's. We can say that the z's make a convex polygon, right? So if they make a convex polygon, now we can talk about the inside, right? Now, so you see, if I say this all projectively, I have three-dimensional vectors modulo GL1. So I have some z1i up tozni. So I runs from 1 to 3. These are three-dimensional vectors, projectively. In order for the polygon to be convex, I have to have that all of the minors involving the z's, these external z's, are positive if they're ordered. So that's the first notion of positivity that I have to have. First, the external data's got to be positive. Once I make the external data positive, there's a second thing I can do, which is talk about the points on the inside of the polygon. And the points on the inside of the polygon are just the same as we had before. They're y equals c1 z1 plus cn zn, where the c's are also positive. Okay? So we see that something as basic as the notion of the inside of a polygon involves an interesting jamming together of two notions of positivity. So let me say it in this example. I have a region in Y space. So this is G13, just two-dimensional projective space. This is, so I'll write it like this, is CAZA. The C's are in the positive part of G1n. But the Z's can be thought of as being in the positive part of G3n. Okay. So the external data is positive. The C's are positive. And I combine two positive things together to define a region inside G13. So that's the inside of a polygon, jamming together positive G1n with positive G3n. OK, is that clear? Trivial inside of a polygon. All right. So now let's consider the first generalization of this. The most obvious generalization of this is to just go to a higher dimensional space. So let's just make I run from 1 to 4, 1 to 5, just higher dimensional vectors. Let's say we make it run from 1 to 4. Actually, 1 to 4, it's a perfectly fine definition. Sorry, let me say one more thing about this. So here, of course, it gave us the notion of the inside of a polygon. We like the inside of a polygon, maybe. But independent of that, there's a good reason to make this and that positive, which is that if you want to combine z's and c's, I mean, if you want to talk about a linear combination of z's and have a projectively well-defined notion, it's very important that it's impossible for the sum of these guys to add up to 0. If they could add up to 0, it wouldn't be well-defined projectively. So you have to make some arrangements so that it's impossible for the linear combination of the z's to add up to 0. And the arrangements you make is you demand that the z's are positive and the c's are positive. And that makes it even possible for it to be a well-defined notion projectively. So even independent of our desire to make it look like the inside of a polygon, if you want to do something as basic as just consider linear combinations of external data, to make it well-defined projectively, you need some kind of notion of positivity. Otherwise, it's not guaranteed to be well-defined. All right. So let's now go up from, let's make this a 4-dimensional vector. Already there's a little problem, because remember I told, so whatever this object is, the polygon has a nice cyclic structure. But if I runs from 1 to 4, this won't have a nice cyclic structure, because remember, the z's are going to be now in the positive G4n. But because k is now even, when you do the cyclic shift, the last guy picks up a minus sign, whereas this guy does not. So that's not going to have a nice cyclic structure. So the first new case, which has a nice cyclic structure, is I runs from 1 to 5. Right? So we're just doing something in P4 now. We went from the polygon in P2 to something in P4. Right? So exactly the same formula. Now ZA1 through ZA5 is positive. And that's it. And the C's are a positive. So they're just in positive G5n. So the Y now lives in P4. OK, now this is already a little harder to visualize. Okay? But, well, for the sake of time, I won't go through this exercise. It's harder to visualize, but just from that definition, it's very easy to see where the boundaries of this space are. So the boundaries are some 4 planes made out of z's, z, za, zb, zc, zd. So you pick 4 of the z's. But quite remarkably, as a consequence of the positivity of the c's and of the z's, you find that the boundaries of this region, of this positive region, are all the 4 planes, are all the points y, when y is in the 4-plane zi, zi plus 1, zj, zj plus 1. So this generalizes the fact that for the polygon, the boundaries are I plus 1, 1, 2, 2, 3, 3, 4, and so on. The generalization of that to this object are these 4 planes, I plus 1, jj plus 1. Now that should ring a bell from amplitudes. Remember, I plus 1, jj plus 1 were where the poles of the amplitude were. And in this dictionary that I'm not telling you for how to convert this geometry into formulas, the poles of the amplitude correspond to going to the boundaries of this object. So the fact that the boundaries are I plus 1, jj plus 1, that's locality. Locality is a direct consequence of positivity. It's the 2-line argument, which I will suppress for the sake of time. Okay. Okay. So, and in fact, you can triangulate this object. You see here we can triangulate it. And incidentally, I should say, this is a 2-dimensional space. The space of C's is an n-1 dimensional space. So this is a highly overcomplete covering of the inside of Y. So to talk about the sort of pieces, like that triangle would, in an overly heavy-handed language, correspond to a particular 2-dimensional cell of the positive G1n, where you send all but 3 of the C's to 0. And the 3 C's that are left define that triangle. So you see there's a collection of 2-dimensional cells of G1n, which under this map correspond to every triangle in this picture. And you could randomly throw them all together, or that covers the whole space. Or you could do something nicer. You could triangulate it. And one of many triangulations is the sum of 1 I plus 1. Okay? Now we can go to this question. And you can say, what's a triangulation of this? Or what's a natural triangulation of this? And you discover the natural triangulation of this is 1 I plus 1, jj plus 1. Now, if you remember, that was exactly the funny combination of 5-bracket objects that I talked about before that gave us that k equals 1 amplitude. And I asked, why does it have this funny form with the 1 sitting here and this funny I plus 1, jj plus 1 property? And the answer is, that's because the amplitude is the volume of that region. Okay? There's this, I never said anything about amplitudes. I just take this y equals c dot z, nothing else. Look at y equals c dot z. There's a natural notion of volume of this region. And the volume of that region is the amplitude, directly is the amplitude. And this is the natural triangulation of it. So that's why we're putting them together in this particular way. So see, the amplitude doesn't live in the Grassmannian, GKM. Those are the building blocks. They're like the triangles. The amplitude actually lives in this other space. In this case, it's living in G15. I'll tell you what it lives in general in a moment. And each one of the cells of the positive Grassmannian, so each one of those things, which comes from a cell of the positive Grassmannian, that in turn corresponds to one of these black-white pictures that are giving us the space-time process, is literally one of the triangles in this picture. And I'm gluing them together in that way because that's what I have to do to triangulate it. Okay? So it's the answer to a natural question. That is the full content. Everything else is translation and dictionary. That is the full invariant content of what the amplitude actually is. Now, in fact, in this case, what happens if I go to the boundaries? I told you that this is a projective space. It's P4. And if I go to the boundaries, well, the boundary is just I plus 1, jj plus 1. Okay? So in this case, the boundary is extremely simple. I just go to the boundary, and it's the 4-plane I plus 1, jj plus 1. All right. Now, let's do another obvious generalization of this. Instead of having, yes?
You excluded the 4 case when the determinant was not positive.
Sorry? Yes.
So what happened with that case?
Sorry, what?
There was a case where you didn't get positive.
Oh, yes, yes. Okay.
So does it still have meaning?
It does have meaning. So I still haven't told you how to turn this into a formula. Okay. So maybe I'll quickly tell you how to turn it into a formula just for the case of the polygon, even for the case of a triangle. See, if you have a triangle, you have 1, 2, 3. So it depends on z1. So the data is z1, z2, z3, and there's y, and all the y's that are the positive combination of these things are the inside of a triangle. Now, associated with that picture and with its geometry is a certain 2 form. There's a 2 form, omega, which I'm going to define the properties of this 2 form on this real slice, but it's a complex 2 form. Once you know what it is, you can evaluate it anywhere you want. It has nothing to do with positivity. It's a complex thing. But it's a complex thing that has a special property that's easy to describe in this real slice. And the special property is that this 2 form has logarithmic singularity. It's associated with a region P. In this case, the region is just a triangle. But it's a 2 form which has logarithmic singularities on the boundaries of P. Okay. Now, what that means is extremely trivial. It means that if you come up with positive coordinates, so what positive coordinates means is that, for example, in this case, it's literally, for example, I can take y equals z1 plus alpha z2 plus beta z3. Very concretely, and alpha and beta are real and positive, right? So if alpha and beta are real and positive, I range over the entire inside of the triangle, modulo accidents at the boundaries. But anyway, so OK. So that's great. So these are positive coordinates that cover the inside of the triangle. And this 2 form is just d alpha over alpha, d beta over d beta over beta. That's what it is in this particular coordinate chart. And more invariantly, it's y dy dy over y12, y23, y31, 1, 2, 3 squared. Okay, so that's a nice 2 form, which has logarithmic singularities on the boundary of that region. Now, that's for a triangle. Let's say I want to come up with a form that has logarithmic singularities on the boundaries of this polygon. It's very simple. I just triangulate the polygon, and I add up all the forms for each triangle. So once I've understood the space and triangulated it, the form comes along for the ride. It's just the sums of the d logs of the positive variables for each one of the coordinates of the triangulation. Okay? Now I have a function. Now I have a function of the y's and of the z's. Okay? And this is almost the amplitude itself directly. Okay? But now you're asking for a now there's data. There's z's, there's bosonic variables, there's y's. Now I have to tell you a little bit more about how I go from this purely bosonic information to a function of bosonic and fermionic variables, because the whole thing is supersymmetric. And that's another slightly interesting step. So in fact, this is a way of talking about supersymmetry which is rather novel. We don't do supermanifolds. There's no super anything. It's all bosonic geometry. But supersymmetry is treated in a quite different way. Instead of dealing with, for example, instead of dealing with things in P3/4, which is the usual way of doing supersymmetry, we actually we add many more bosonic variables. And then we extract supersymmetry in a quite different way. So that would take a little longer to explain, but it's a very canonical and straightforward thing. In any case, at least now you see how you have functions, right? So, but you see, once I have this form, I don't care what the z's are. These can be anything they want. They can be oriented anything they want. There's this nice form. The form has a property that if the z's are on the positive part, then it has logarithmic singularities on the boundary of the polygon. But once you know what it is, you take it anywhere you like. All right, so that's what we're going to do. We're going to first define a region, and after we define the region, we define a form with logarithmic singularities on the boundary of the region. That form is the amplitude, okay? And I call it the volume because this form is the kind of a dual notion of volume. It's not actually, anyway, it's closely related not to the volume of the polytope of the polygon, but the area of the dual polygon in this case. But in any case, it's worth calling volume because it has the same additive properties as volume. If you have 2 regions that are disjoint, the sum of the 2 forms is equal to the, anyway, it has all the same additive properties as volume. OK. OK, so but modulo that dictionary, I can now at least describe to you. So if you don't care about that part, a part that should be of independent interest purely as a nice part of the Grassmannian, and I'll just say this and the end, is just this region of the Grassmannian. So we already did y equals CAZA. Now we're just going to do one last thing. Instead of having one y, we're going to have k y's. And instead of looking at the points y, individually, we're going to look at the k-plane that's spanned by the y's. So everything is as Grassmannian-like as possible. Okay, so alpha, there's ky. So alpha runs from 1 to k. This I runs from 1 to, well, in general, just purely mathematically, it could be m plus k for any m. And that's the space. Okay, so y lives in gk, k plus m. This is the analog of the inside of the polygon. C is now going to be in the positive part of gkn. And the z is going to be in the positive part of gk plus mn. And for the similar reasons as we talked about before, we should, for the object to be cyclic, we should have that m is even. These positivities guarantee that this is a well-defined projective statement. So that gives you a well-defined plane. And that's it. So this is the generalization of the polygon, the inside of a polygon, into the Grassmannian. The volume of this object is the tree amplitudes, all the tree amplitudes of the theory. Okay. So if you want to compute that, you have to triangulate that region. Now the triangles are much more interesting, because now the triangles are certain cells of the positive Grassmannian. They're not just the simplices like we had when it was G1n. Now these triangles are much more interesting. There's many kinds of triangles. Well, we understand everything about the positive Grassmannian. Each cell of the positive Grassmannian of the appropriate dimensionality turns into some region in this GKK plus 4 space. And if you ask, you take those terms in the recursion relations. You ask, what do their images look like under this map? You find this term goes into that part. That term goes into that part. None of them overlap. The collection of all of them beautifully cover the entire positive space. Okay? So the tree amplitude is the volume of that region. That little, yeah?
Tree amplitude, you mean the sum tree amplitude?
The entire tree amplitude. The entire, well, it's a tree amplitude, but yes, but not one diagram. The entire tree amplitude is the volume of that space. Okay, you give the z's, it's just the volume of that space. And in fact, even without doing the full computation, you can see locality and unitarity emerge as a consequence of positivity. Let me tell you what happens. So I skipped showing it in the previous example. It's so simple. Let me just take 2 minutes to show you how locality comes out, and then I'll just say one more thing here, and we'll end. So let me go back to the example where we had y equals c1 z1 plus cn zn. And now this lived in P4 rather than in P2. I want to see why are the boundaries ii plus 1, jj plus 1. So in order to explore what the boundaries are, I want to look at, so I want to see, is ZA, ZB, ZC, ZD for some A, B, C, D. I want to see, is that a boundary? To see whether that's a boundary, I want to look at this 5 bracket made out of Y, ZA, ZB, ZC, ZD. It's the analog of looking in the polygon. Let's say I want to see, is 1, 3 a boundary? Well, if y is in here, then y13 is negative. If y is in here, y13 is positive. So y13 doesn't have a fixed sign. That's why 1,3 isn't a boundary. But 1, 2 is a boundary. Y is always on the same side of 1, 2. So we can determine where the boundaries are by just looking to see whether this expression has a fixed sign or not. Okay, that's all. Well, it has a chance of having a fixed sign because I'll just expand it. That y is c1, 1 ABCD plus c2, 2 ABCD plus cn, n ABCD. And these c's are all positive, so it has a chance. And remember that all these 5 brackets are positive, provided that these guys are ordered. But now you see what the problem is. If A, B, C, and D are random indices, so this is index space, 1, 2, 3, here's A, B, C, and D. If A, B, C, D are random, then if this index here, if it's there, the term is positive. If it's in between A and B, it's negative, because I have to reorder them. If it's there, it's positive. If it's there, it's negative. So some of these terms can be positive, some of them can be negative. It does not have a fixed sign. With one unique exception. When A, B, C, D looks like I plus 1, J plus 1. Because then it's either on this side or it's on that side, and you jump over 2 indices, so you don't change the sign of the minors, and everything is positive. So that's how we conclude, just as a simple consequence of positivity, no fancy analysis, just as a simple consequence of positivity, that the only boundaries are I plus 1, JJ plus 1. Okay? Under the map, because remember, the amplitude is the form of logarithmic singularities on the boundary, then the poles of the amplitude are when y approaches the boundary. And that's how we discover that the boundaries are I plus 1, jj plus 1, when those things become collinear, when they become coplanar. Okay? Exactly the same argument goes through in this case. All that changes, instead of those c's, you get many more indices here. But the argument is identical. These become the positive minors. That's why the Grassmannian has got to be positive. And exactly the argument goes through. And so we get, in general, that the poles are local. So that's locality from positivity. Now, something that I won't show you, but also emerges very quickly, again, without solving the problem in full generality, just exploring some consequences of positivity, is what this space looks like as you approach the boundary. And what you discover as it approaches the boundary is it has one piece, which is where are I plus 1, jj plus 1 on this plane. But the rest of it splits into two pieces, a left piece and a right piece, exactly as the amplitude does. Okay? And that's another, it's a consequence of, so literally, it's saying that these matrices C, as you approach the boundary, you can arrange so that some top component is non-zero only in I plus 1, jj plus 1. The rest is 0. And as a consequence of all the minors being positive, it literally has to factorize into two pieces, a left piece and a right piece, and 0 and 0. And this precisely mimics, not mimics, it gives you the splitting like that. That, again, we normally attribute to particles going on shell because they're propagating in space-time. There's no space-time. There's no Hilbert space. There's no path integrals, no gate symmetry, none of that stuff. There's just this geometry. And the geometry has all the singularities, all the properties that we normally attribute to that unitary local evolution locally through space-time. All right. So anyway, so that's the simplest example of the amplituhedron, is this object. Just generalizes the polygon. And let me just say in words, but spend no time on it, that you can now, there's a natural question to ask. If you have this big, gigantic object with a humongous number of points, what if you want to forget a bunch of the points? What if you just don't want to look at them? You just want to look at fewer points. So forgetting geometrically means a projection. There's a very natural way of projecting away from many of the points. If you project away from many of the points, the resulting object that you look at isn't just slicing those points off because they have to be, they're all positive with respect to each other. So in the fewer space that you're looking at, there's more positive constraints on it. And it's some additional variables that remind you about the ones that you were, that you were ignoring. Looking at that resulting object, that projected object, is loop amplitudes. Okay? So this was tree amplitudes. And forgetting particles is loop amplitudes. So in a very literal sense, it's a hidden variables theory. The quantum corrections are coming from forgetting things. Of course, none of it's local. There's no space-time. There's none of that, so it doesn't violate any rules. But there's a very natural geometric forgetting operation that turns into loops. And so I can finally define the whole amplituhedron, at least mathematically. I'll just define it on this board and just claim that that the volume of this object is the whole amplitude. So that was the trees. So we have a k plus 4-dimensional space. We have a k plus 4-dimensional space. First, we have a k-plane in k plus 4 dimensions. Okay, so this is our friend y. This is our k-plane in k plus 4 dimensions. Now, conjugate, orthogonal to that k-plane in k plus 4 dimensions, is a 4-dimensional space. And for tree amplitudes, that 4-dimensional space is empty. Okay? Loop amplitudes turn out to populate that 4-dimensional space with a bunch of lines. So we have L lines in P3, or L2 planes in G24. If you have L loops, you have L lines. Okay? So I can call this one, A1, A2 for the first loop. I can label that line by 2 points on the line. I can label this line by A1, A2 for the second point, and so on. So I have L lines. Right? And I have my z's. My z's are k plus 4-dimensional vectors. Okay? So I runs from 1 to 4 plus k. Remember, this looks like way too many bosonic variables, but I told you that there's this new way of doing supersymmetry, that the p3 plus k turns into p3/4 in a canonical way. But let me not tell you how that's done. Okay, so I have these guys, and they're positive. So the external data is positive. Now, in this space, so the space is k planes in k plus 4 dimensions with L lines in its 4-dimensional complement. in that space, there's a region. There's a region given by y equals c dot z, and each one of these a's. So a is equal to, let me call it L dot z. So this is a 2 by n matrix. And this is for the first loop, it's L1. And up to the nth loop, it's LL. Okay? So there's this region in that space where there's a positivity constraint that if I look at this K, if I look at this matrix C and all these L's, all the minors you can possibly make are positive. Everything you can possibly make is positive. Okay? So it's the maximally positive part of this positive space. So that gives you a region inside this space. The volume of that region is the L loop amplitude. And there's a simplest possible version of this, which is where k equals 0. You don't even have the k-plane. Now you just have L lines in a 4-dimensional space. That 4-dimensional space is now the conventional twistor space. See, in this picture, twistor space isn't even a God-given thing. There's not one P3 sitting there. The P3 is always conjugate to this k-plane. So this k-plane moves around, the P3 moves around. There isn't even a fixed twistor space. So as I said, twistor space is very kinematical in this picture. But we can go to k equals 0. These are the simplest loop amplitudes. And yeah. The n, it's because ZA runs from 1 to n. So there's n of them. And this is GKN. So these are all n. That's k. This is 2, 2, 2. And you take this big k by 2L by n matrix. Every minor you possibly can is positive. Okay? I should say every minor including C. So C is positive. CL is positive. They all have to include C. But all the ones including C and any other guys are all positive. Okay? And the volume of that space is the amplitude. By arguments analogous to what I showed you, you can show the singularities of this object, make it local and unitary, including the unitarity statement at loop level, not just at tree level. But just to give you a flavor, and I'll just pose this as a little math problem. It's a math problem that's possible to give to a junior high school student. And I thought, because of that, I would be able to solve it quickly. But I've been working on this math problem for 3 months. So if one of you can solve it, please do. And you'll also have solved for the 4-particle amplitude to all loop orders in this theory. So let me tell you what this question turns into for the simplest case of n equals 4 particles. Okay? N equals 4 particles. You see, the tree level story is a generalization of the positive Grassmannian. Okay? But the loop story is, the whole story is this. But the loop story is quite different looking than the positive Grassmannian. We can just stare at these L lines in this 4-dimensional space. And so we have a kind of a positive structure on the space of lines. And now these lines is totally permutation symmetric. There's no cyclic ordering on them. I just have L lines. So I have some nice structure in the space of L lines in P3. But I have to demand that all their minors are positive. Okay? So they're all individually positive, and they're all positive with respect to each other. So if I specialize the case of 4 external particles, it's particularly simple. Each one of these L's is a 2x4 matrix. It has to have positive minors. There's a very simple parameterization that guarantees that all the minors are positive. You can check that all the minors of this 2x4 matrix are positive. If I have L loops, each one of them looks like this. So you see there's 4 variables, x, y, z, w, associated with each loop momentum. That's the same 4 as L0, L1, L2, L3. So that's 4 loop variables. And all of this statement just turns into the following problem. So let me group these guys together into a little 2-dimensional vector A, which is xi, yi, and B, which is zi, wi. So I flipped it around, and I removed the minus sign. Okay? So first, I have these 2-dimensional vectors. First, all these x, y, z, w's have got to be positive. That's a statement that each one of these minors is positive. So you can think of these as kind of A points that live in the upper quadrant, 2-dimensional upper quadrant, and B-type points. So here's A1, A2, A3, and you have B-type points. I'll denote by x's that live in the upper dimensional quadrant. So you have 2 kinds of points, A points and B points that live in the upper dimensional quadrant. And the second condition that all of these minors are positive turns into the very simple condition that for any pair I and j, AI minus AJ dot bi minus bj is negative. That's it. So it's the moduli space of all points that satisfy these two constraints. They live in the upper quadrant. And this is just saying that if you take the line from 1 to 2 for the A's and the same line from 1 to 2 for the B's, that they're going in opposite directions. Okay? That's all. That's it. So triangulate the space. I mean, find coordinates on this space. Fully understand this space. Triangulate it means find a set of positive coordinates which together cover the entire space without going through each other. Yeah. 1 to L, where L is the number of loops. So if you want 2 loops, there's just 2 A's and 2 B's. Right? So triangulate that space, and you're done. You have the L loop amplitude. So that's the problem we've been trying to solve. You can do it by hand for low L. And notice nowhere here, you see, in our previous story, there are recursion relations. There are things that even vaguely look like Feynman diagrams. They weren't Feynman diagrams. They had black and white vertices, but they had a width of the underlying quantum field theory picture. Here, it's all gone. It's just totally gone. You're playing with these inequalities. Nowhere in here is it manifest that the answer to this question has anything to do with summing planar diagrams. But it does. It sums planar diagrams. But it does it without drawing any diagrams, in fact. Right? So we've done it by hand up to 4 loops. Okay? And you can really do it by hand. I mean, it's just a simple little exercise. What we're trying to see is find the general structure. There must be some, in the case of the ordinary positive Grassmannian, there's a whole beautiful story of, I didn't tell you, all the cells, positive coordinates, cluster coordinates. There's a cluster algebra structure behind all of this. So there's a huge, powerful machinery that tells you exactly what to do ahead of time. There must be some analog of that here. There must be a smarter way of doing this than we've been doing. Even though, so we spent 3 months trying to do it in both dumb and smart ways. The smart ways aren't going anywhere. The dumb ways gradually go somewhere. But even though we haven't found the whole problem for all L, A, we believe it's possible. But B, we've computed special cases. So special cases means, for example, just to give you an example. Let's say all the A's and B's are on the x-axis. So that's a much simpler problem. If all the A's and B's are on the x-axis, this is a far more trivial problem, because this inequality just turns into xi minus xj, zi minus zj is negative. Which just means that if the x's are ordered, let's say I can always, without loss of generality, say that the x's are ordered like this, x1, x2, x3, up to xn, that the z's have got to be ordered in the opposite way. zn minus 1, up to z1. Okay? All right, so the solution to this inequality is just x is ordered like this, z is ordered like that. Then you ask for the form of logarithmic singularities in x and z on that space, and it's extremely simple. Saying that the x's are ordered in that way is saying that the form is dx1 over x1. That just says that x1 is positive. dx2 over x2 minus x1. That says x2 is bigger than x1. All the way up to dxn over xn minus 1. But then you've got to order it the other way around for the z's. So dzn over zn, dzn minus 1 over zn minus 1 zn, all the way up to dz1 over z2 minus z1 minus z2. Okay? So that's the form with logarithmic singularities on that space. And that, so what does making these things special correspond to? Moving to boundaries here, remember I told you moving to boundaries is taking singularities of the form. So this is literally taking a residue of the underlying differential form on this special configuration. Those residues are otherwise known to amplitudologists as cuts. So we're computing certain cuts of the amplitude. In fact, this cut is a very simple one. It's a cut to an amplitude person which makes every single loop momentum null separated from the point 1. Okay? Now, as an amplitude person, as a mathematician, you've never heard about this. But as an amplitude person, you know there's a unique set of graphs that has that cut. And no other graphs have that cut. Those are the ladder diagrams. Of course, here you put in an awful lot of extra information about n equals 4 super Yang-Mills, no triangles, boxes, et cetera, et cetera. But this is a unique set of diagrams that has that cut. Okay? And you see, that's exactly this form. I mean, I have to tell you a little bit about what the dictionary is, how to interpret these x's. But that's exactly giving you this ladder structure. The x's are ordered, the z's are ordered in the opposite direction. And that's actually telling you that there's not only is it a ladder, but one has one end and the other has the other end with an x and a z. Okay? So it's utterly trivial to compute infinite classes of cuts. This is a totally trivial one, which we knew how to do beforehand. But there's an infinite class of others that we have no idea how to do from any other point of view that we can just write down on one line. We verified that they're true up to 5 and 6 loops where the results are known in the literature, but then we know them to all loop level after that. So it has, so you can really do computations like this as well. And something else I should say, which this relies on a sort of remarkable identity about dot products. But anyway, there's some identity about dot products that shows you that there's another interesting cut. There's a cut where you take one of the a's and you put one of the a's on the y-axis and the corresponding b to the x-axis. Okay? So that cut corresponds to a physicist to the unitarity cut. To take one loop and doing the double cut. And then you can show, if you take this problem, you take one of the a's to the x-axis, one of the b's to the y-axis, the solution to this problem splits in two. It splits in two to a solution of a lower point problem on the left, a lower point problem on the right. And the classic textbook unitarity double cut is a direct consequence of positivity. Okay? Even without, yeah.
Lower loop now.
Lower loop, yes, sorry. Lower loop. And you have, in fact, you've got a sum over all of them. So you see the entire structure that's got to be there. Again, of course, it's not a surprise because the underlying, I mean, we've proven unitarity for the whole underlying object, but it's even nice to see in this limited little problem, just for the simplest MHV amplitudes, 4 points, that textbook unitarity is a consequence of positivity. Just, you can forget about everything else I told you. Just focus on this little geometry problem. That little geometry problem is all the juice of an interacting quantum field theory in 4 dimensions. And trying to understand where it comes from is, I think, going to be interesting. Anyway, so I've gone on very, very long. I thank you for your forbearance. I should say that there's many, many open questions in this business. This is, of course, yes. This is so baby, it's not even worth talking about. I'm sorry I spent 2 hours talking about such a worthless problem. But yes, it's the leading order in 1 over n. It's planar. But I'll say one thing. So something that people often say is that, oh, this theory is integrable. This is why this is all happening. You know, it's all special to integrability and so on. You'll notice not once did I say the word integrability, right? None of it seems to look like standard integrability techniques. None of it looks like you make and guess ansatz. You can explain it to your grandmother. That's another thing which is different than the usual integrability story, right? It's not some, but it doesn't have that. But in fact, I talked about it only because someone said the Yangian exists, okay? I didn't tell you the interpretation of the Yangian. The Yangian, from the point of view of the, and that's just a property of the old positive Grassmannian story. Remember I told you the Yangian symmetry is a property of the individual building blocks. The individual building blocks are Yangian invariant. Why would you even suspect from this point of view that there's an infinite dimensional symmetry? Well, there's such a stupid symmetry, you don't even pause to care about it so much. But if you did, you'd say, oh, I can do these positive diffeomorphisms on the space. I can just move points around the space without changing the boundaries. That's an obvious symmetry. That infinite dimensional symmetry is the Yangian. Okay? So the Yangian has an utterly trivial origin in this picture. But like I said, it's so trivial, it doesn't buy you anything. It's not good for anything. It's not like you're using it all the time. It's sort of the other way around. There's some structure, and then you notice it has this infinite dimensional symmetry. But you don't care much. It doesn't help you. It's not helping you at this point. There is a place where I think it will help you, which is in carrying out the actual integrations. Okay? Integrability should be useful for doing the integrals. That's, you know, that's where integrability, where the word came from to begin with, right? But this is about, but the structure before that, and in particular the structure that's telling you about this different origin of locality and unitarity has nothing to do with integrability, as far as I can tell. Of course, until we see it in another example, I don't know. But it could just be an accident. But the reason I suspect it's not an accident is that if we go back not to this bigger story of the Amplituhedron, but just to the building blocks, just the story of the positive Grassmannian, the link between the positive Grassmannian and these on-shell processes is totally universal. It has nothing to do with n equals 4 super Yang-Mills. It just has to do with gluing together elementary 3-particle vertices to build more complicated objects out of simpler ones. And if the theory is planar, it's always associated with the positive Grassmannian. If it's a random theory, it's associated with some structure in the Grassmannian that we don't understand. We're starting to understand, but we don't understand. If it's planar, no matter what the theory is, non-supersymmetric, n equals 0, it's associated with the positive Grassmannian. So that connection is universal. There's a form on the positive Grassmannian which is very special, all it has is singularities on the faces of the positive Grassmannian. That's this form that we keep talking about. That's special to n equals 4 super Yang-Mills. When you go beyond n equals 4, the form is that multiplied by one other piece. And that one other piece has singularities on another part of the positive, on another part of the Grassmannian. In fact, not the positive Grassmannian. It doesn't even intersect the positive Grassmannian. There's two regions in the Grassmannian. Positive Grassmannian, new part. They literally do not intersect each other. And what are all those other singularities? The physical interpretation is all the ultraviolet singularities. Okay? So the computation of the beta function, you can get the 11/3 from some computation in the Grassmannian localized on that other guy. The fact that they don't intersect is UVIR decoupling from the point of view of the space-time theory. Right? So anyway, it's all sitting there. So the building blocks are sitting there. The fact that you can compute things recursively is true beyond n equals 4 super Yang-Mills. The fact that there are zillions of ways of representing the amplitude, all by putting these objects together in different ways. That's true beyond n equals 4 super Yang-Mills. I would find it very surprising that only for n equals 4 super Yang-Mills does all of that gluing together have the interpretation of the volume of something, and the second you go beyond it, it all breaks apart and has no interpretation of that sort. That would be shocked. But we don't know. Beyond planar is even more interesting because, you see, again, you would think that you go beyond planar and everything goes to hell. In fact, all the indications are that it's the other way around, and that there's something missing in the planar story that only makes sense when you go beyond the planar limit. For example, you could say, is there anything left to be desired? I mean, if there's a lot left to be desired, but is there anything left to be desired even morally in our understanding of these planar amplitudes? And there is, because here there's a cyclic ordering of the external particles. And you would think there's a separate object for ordering 1, 2, 3n, for ordering 2, 1, 3n. So for all the orderings, there's a separate object. And you would have no reason to suspect they have any relation with each other. But we know they have remarkable relations between each other. There are these old relations like these U1 decoupling identities. There are these more magical recent versions like Zvi and friends, these BCJ relations that relate all the different orderings with each other. These are sort of amazing. This is just as a state. Even forget about going beyond the planar limit. There's relations between planar objects that we don't see in the planar limit in each term separately, that we only see somehow when we think about them all together. So where are those relations going to come from? We've understood just inside one given planar sector that all these relations are sort of triangulating something. They're all different. They have some nice geometric interpretation as cutting some region up in different ways. Again, I would find it very hard to believe that those identities have an understanding like that, but then the identities between the different sectors are just, no, we can't understand them at all. We've got to go all the way back to the Lagrangian. No way. What must be is that each one of these planar things is itself the face of some bigger object. And that and all the other orderings are gluing together into a more master object that then nicely glues together beyond the planar limit. I mean, I'm telling you the sort of fantasy for how this might go. But I'm also giving you the circumstantial evidence that something like it should exist. So there's sort of data in the structure of the answer that hints that there are still things that are left to be understood, even in the planar case, which wants you to go beyond the planar limit. And another thing that you know very well is that as we go beyond the planar limit in n equals 4, we have reason to suspect the theory gets nicer. We have S-duality, which we don't see in the planar limit. So there's more symmetries that need to come out. There's more structure that needs to come out beyond the planar limit, not less. So, but anyway, so that's, it's all fantasy for now.
Okay, let's thank Nima for this.
Regarding this story of the beta function, because I wanted to ask you.
Yes.
In
No,
the discussion.
of course not. That's
And
the
yet
whole
it
point.
is crucial in the discussion of the beta function.
It's not true.
Well, we know that there are 3 loops.
Huh?
We know that there are 3 loops. We start
Well,
to
you
gauge
can compute the beta function. You can compute the beta function using these unshelled
But we
techniques.
start to see
Right.
gauge dependence.
There's no gate symmetry. Gate symmetry doesn't exist.
Scheme dependence.
Yeah, there's scheme dependence. That's a totally different thing. The scheme dependence is a totally different, completely human-made artificial thing. There's it's not. First of all, it's not gauge dependence. It's scheme dependence. Secondly, if you have a fixed theory that you're talking about that's regulated in a fixed way, then there's a fixed notion of a beta function, which is Wilson's notion. How you change the bare couplings with the regulating parameter to keep the physics fixed. So that Wilsonian beta function is a totally physical invariant notion. Then there was some stupid
but
redefinition of
to do
couplings that
that-
you can do, which is what we normally call scheme dependent. So that's completely
Yeah,
arbitrary.
but that Wilsonian we know how to do non-perturbatively using a lattice or something like that.
No,
But how
even-
do we inject it in the language of graphs? I mean,
Oh, it's completely straightforward. I mean, so you choose any regulator you want. Choose dim reg. Choose any regulator you want. Once you fix a regulator, there's a notion of a Wilsonian renormalization group equation. It has nothing to do with the lattice. It has nothing to
that
do
you are
with-
doing
yeah.
perturbation theory.
Yes.
And it's no longer what you are saying. This is 1 over n.
Well,
Business which
perturbation
is
theory
like,
is one of. I mean, we're doing perturbation theory in the large n limit. Perturbation theory in the large n limit is a standard perturbation theory in the Tooth coupling. And it's just that we throw out non-planar
but
graphs.
that
that's all.
coupling that you sit in G square n,
Yes.
which coupling is that? That's the bare coupling, the running coupling. What is that?
Well, so you pick
In
a
a
theory.
non-supersymmetric theory, it
It has nothing to
runs.
do with supersymmetry. Yes, of course it runs. Even in supersymmetric theories, it runs. The second you go beyond n equals 4 superiotic nodes, it runs. So yes, we can go to large n, and n equals 2 superiotic nodes, n equals 1 superiotic nodes, n equals 0. Perfect. Okay. So there's a G squared n. Now we have there's an ultraviolet regulator. You can regulate it 100 ways. You can use dim reg, dr bar. You can embed the whole thing in an n equals 4 supersymmetric theory. Give a big mass to the additional chiral. There's lots of ways of regulating it. But in a fixed regulator, there's now a physical question, which is how, once you change the regulator, how do you have to change the couplings to keep the physics fixed?
Right.
That's Wilson's question. It's nothing to do with the lattice. That's Wilson's philosophy for thinking about the renormalization group. That has a well-defined answer. That's a totally sharp, well, there's no scheme dependence, nothing. It's a perfectly sharp, well-defined answer. It's a property of the physics. It's a property of the full theory, including the regulator. And then you compute the beta function. You get an answer. What we normally call scheme dependence is something else. It's how we convert that useful information you get from Wilson into renormalized perturbation theory. Renormalized perturbation theory involves some arbitrary choices for what you want to call the coupling constant at low energies, rather than the God-given couplings that define the theory together with the regulator as the whole thing. So yes, but in any case, finding the beta function is a question of computing the amplitudes and finding the ultraviolet logarithmic divergent pieces to them. You can do it at 1 loop. You can do it at 2 loops. If you're very powerful, if there's V, you can do it to 17 loops. Sorry, 5 loops. 4 loops. Yeah, so 4 loops. Yeah, but yes. But it's a nice thing. It's not even the 1 loop, the famous 11/3. The famous beta function at 1 loop. You can really get beautifully from unshell methods. No ghosts. Of course, no gate symmetry. There is no gate symmetry. That's the whole point here. You see, when you start eschewing the usual picture of local evolution through spacetime, you don't need gate symmetry. Gate symmetry is a crutch we use because we want to describe the physics in a local way, manifestly. Nothing wrong with it. It is local. We're not saying it's not local, but we're saying that it's interesting. There's a way of talking about it where locality comes out at the end, and other things are brought to light in the beginning. And if you're going to do things that way, of course you're not going to talk about gate symmetry. Why should you? Gate symmetry isn't a physical property of the world. It's a property of our imagination as theorists for describing the physics in a particular way.
So I'm more practical, just to go
Yes.
back to the picture. Two of the momenta in one of these two
Yes.
momenta that are
Yes.
ordered near
Right.
each other become parallel,
Yes.
the amplitude gets big.
Yes.
So
That
I
yeah.
see some of these DC overseas, but where did this happen in the formula?
Yes. So so actually.
So that does that mean that there's a volume that's getting big?
Yes,
Am I
it tells you that there's a volume which is getting big, but actually, it tells you that there's a volume that's getting big, but there's a nice way of thinking about that in this picture, where instead of moving, I didn't tell you in enough detail what the y's are, but the y's you should see normally when you do things projectively. There's a to get the actual. For example, when we say the variables are 1z, we're choosing a line at infinity, right? And that's what defines what we mean by those lower components. In that picture, you keep the line fixed, and let's say you want to move the data around, you move the data around. So that's the normal way we have of thinking about it. You approach a factorization limit, you're actually moving the momenta around in order to make the sum of the momenta go on shell. You want to do what you do, you take a soft limit, you take a collinear limit. You're moving the momenta around, right? But in this picture, there's a dual way of thinking about that, which is quite a bit more powerful, which is you leave the momenta where they are. Everything is fixed. The external data is fixed, but you move this line at infinity around. Okay? And what you think of as the collinear limit is when this y goes like, when this y contains I plus 1. That's the collinear limit. When it contains I plus 1, jj plus 1, is when it's the multi-particle factorization limit, and so on. So going to different boundaries of the amplituhedron correspond to the different physical singularities of the theory. And in particular, the soft limit or the collinear limit, as your thing, is a very simple one. It's even simpler than these factorizations that I was talking about. It's like, for example, you want to just remove one particle. Okay? So removing one, you're removing one particle, you literally sort of project away from one point. You pick one point and just in the usual sense of projective geometry, just project away from it. And doing that just takes the soft limit. Beautifully takes the soft limit. In the language of these k by n matrices, it's saying that you said that y is equal to some big c dot z, but you want to project away from one point. So that means that you want to talk about the y's which just don't point in that z direction. So that means that I'm always free to say that the bottom component of the y is just that z, and the rest of the y is orthogonal to that z. But that means that the C matrix now has to have this funny form, like zeros. I mean, I can always, by convention, put zeros there. Okay? But zeros everywhere there and a block there. But you see, positivity of the whole matrix just means that the submatrix is positive. And that's it. That's the one lower particle, one lower k amplitude. So it's an even simpler version of this sort of factorization that I was telling you before, that if you put in I plus 1, j plus 1, just positivity of the whole big matrix forces the submatrices to factorize in these funny ways with lefts and rights. So soft and collinear limits are even simpler from this setup. But they just correspond to going to certain boundaries of this space. But that's one of the novelties. You don't think about moving the data around. You think about what we normally think of projective geometry as auxiliary variables. You move the auxiliary, you move the pointed infinity around. And the pointed infinity then, hitting different boundaries of this thing, of the amplituhedron, probes all the different physical singularities.
Brodsky has argued that factorization breaks down in certain processes.
Oh, that's a different factorization. That's a totally different.
Yeah, but it relates a little bit to this idea of final, being able to describe everything with final state on shell.
Well, I mean, we're very, very far away from that question. We're very far away from that question. I mean, of course, we have massless gluons here, so we're not talking about how these things turn into hadrons. And in n equals 4 superunion modes, they don't turn into hadrons. So that's anyway. But yes, no, we're very far away from those questions. This is all just structures of. I mean, these are properties of perturbative super QCD, perturbative QCD, but there's a long, long way to go. Yes.
Going back to your 4-point amplitude, if I have, suppose I've arranged my A and B vectors appropriately at L loops.
Yes.
And now I want to go to L plus 1.
Yes.
So the naive thing you might think is, well, okay, everything works up to there. Right. Now I can just add 2 more vectors and make sure that, is that wrong?
Yes.
You have to go and restrict.
It is wrong because what's happening exactly. Well, because what is happening, even if you've arranged them to be the same, roughly speaking, what happens? I mean, you don't quite see it in these examples, but if you want to nicely triangulate the space, then what's going on is you've added these extra A's and B's, right? Now, when they're in this configuration relative to everyone else, that's one region. But then when they're in a different configuration, that's another one. So depending on what the rest of the guys look like, even if they're all positive with respect to each other, the way they interact with the last A and B will be different. So what it really means is that what you're going to do is you're going to whatever you triangulate at lower loops, and even inside that triangulation, you have to break it up into different sectors.
Break pieces.
Right, exactly.
Lose pieces.
Exactly. Well, I mean, you don't lose pieces, but
I mean, in terms of these A's and B's.
Right, exactly. So roughly speaking, if you've succeeded, if this is a piece that I'm being very schematic, but if this is a piece that you managed to triangulate at lower loops, you then have to go and further break it up into pieces, right? And in each one of those pieces, the L loops are in a different relation to the L plus 1 that you added to keep it positive, right? So that's why that's why it doesn't have this add one at a time feature. Which, of course, is why we also know from even roughly what the diagrams look like. They do not have that kind of structure at all. If you take certain cuts, it goes down very nicely. So all the cut properties.
So you can't you can't have some analog of a Schwinger-Dyson equation?
Oh, well, there is an analog of the Schwinger-Dyson equation. The analog of the Schwinger-Dyson equation, roughly, are exactly what was used to determine the amplitude not just at tree level, but at loop level recursively to all orders in perturbation theory. So there's an extension of BCFW to all loops. And roughly speaking, it's a Schwinger-Dyson-like thing. I mean, it's slightly more, it's basically a Schwinger-Dyson-like thing. There's nothing very interesting. And you're just using locality and unitarity a little bit smartly. And it's mostly a technical thing to figure out how to really use it, right? But it's nothing deep. It's just basically Schwinger-Dyson. You do that, you can recursively determine it. Now it's powerful. You can use it. It's good. You can generate data. It's great. But it's always been, and it was useful to be able to do it. In some sense, it solves the theory recursively, right? At least for the integrand. But it's always been clear there's something ugly about it, because let's say you want the 3-loop 4-particle amplitude. If you want to determine it recursively, you have to start from the 10-particle and cubed MHV amplitude. And then you have to take these funny limits, and you're not living in the right space. In the end, you want just some function of these 3 lines in twistor space. Why do you have to start with 10 particles, higher k, do all this crazy stuff? And then also you see that the individual terms, so many of the terms vanish. You don't know why some terms vanish. There's something very non-canonical about it. We understand that quite a bit better now. So you see, this problem is to find that loop level lives directly in the space it's supposed to live. And now, remembering where the bigger structure, we can show that bigger structure satisfies that Schwinger-Dyson equation. So that's why we're sure that it's all right. But despite that fact, you can set up the question directly in the space. And you can ask, in the cases where we know how to triangulate it by hand, does it look like what we get from the recursion relations? The answer is absolutely not. We have no idea how to identify these natural triangulations with what we get from these recursive methods. Maybe they're the same, maybe they're not the same, we have no idea. But it's much nicer this way. It has no, that's what I said, it doesn't even have any remote connection, obviously, to the underlying graphical ideas of Schwinger-Dyson equations.
Completely different question. In the case
Okay,
of
Martin, I suggest to thank Nima again.
Yeah.
And then move to Nima.
Are you available for dinner?
Well, people want